right, lesson 10b, inverses of exponential functions. It says a logarithm base b of a positive number x is defined as log base b of x equals y if and only if b to the y equals x. You can read log base b of x as log base b of x. In other words, the logarithm y is the exponent to which b must be raised to get x. A logarithmic function is the inverse of an exponential function. A logarithm that uses base 10 is known as a common log. A logarithm that uses base e is known as the natural log. You can write log base 10 of x as log of x and log base e of x as a natural log of x, or ln of x. A logarithmic scale is any scale that uses a logarithm of a quantity instead of the quantity itself. We now look toward graphing logarithmic functions and transformations. All right, so we have our parent function. And our parent function is just going to be y equals log base b of x. We have a vertical dilation, which means we have y equals a times log base b of x. Now, this vertical dilation could be a stretch. And in that case, the absolute value of a would have to be greater than 1. Or it could be a compression or a shrink, which means that the absolute value of a would have to be between 0 and 1. We can have a reflection in the x-axis. So that's where we'd have y equals negative a times log base b of x. Or reflection in the y-axis, where we'd have y equals log base b of negative x. We can have translations, where we have y equals log base b of x minus h plus k. Remember, h is a horizontal translation. It's going to go left or right. It's going to do the opposite of what we think. So if it's a minus h, it's going to go to the right. A plus h would go to the left. K is a vertical translation. It's going to go up or down. A positive k goes up, a negative k goes down. And then we could have all the transformations. So we could have y equals a times log base b of x minus h plus k. All right, so example 7. Describe how to transform the graph of f of x equals the natural log of x, or g of x equals log of x, excuse me, into the graph of the given functions. Write the xy rule. All right, so it starts out with h of x equals 3 plus log of x. This is the same thing as saying log of x and then a plus 3. The 3 is not inside parentheses with the x, so it would affect the y. So this is just a vertical translation. Up 3 units. All right, so my rule, the xy rule that they're talking about, is you have xy, then that 3 is going to make us add 3 to the y values, and so the new rule would be x comma y plus 3. So it's kind of like what we were writing at the top of our tables when we'd say, okay, we're going to add 3 to the y's. That's what we're doing, just as an ordered pair form. And so if you wanted an example, so if I had the ordered pair 1, 0, my new ordered pair would be 1, 3. All right, B. B says we have f of x is equal to negative 2 times the natural log of x minus 3. All right, so the negative is going to make us reflect across the x-axis. The 2 is going to be our vertical dilation by a factor of 2. So that's going to be a stretch. And then the 3 is going to be a horizontal shift or horizontal translation. It's a minus, so we're going to go to the right 3. And so our rule with xy, so we can see that inside with x we have an x minus 3, so that means my x's we're going to add 3. And then so my y's just have that negative 2 at the beginning, so it's just going to be negative 2 times y, or y times negative 2. So if we had an example, if I had the ordered pair, let's say again 1, 0. Now I do 1 plus 3, which is 4, comma, negative 2 times 0, which is 0. That would be my new ordered pair. And then C says y is equal to log base 3 of 2 minus x. This is the same thing as saying log base 3 of negative x plus 2, which is the same thing as saying log base 3 parenthesis of a negative parenthesis x minus 2. So if you common factor out that negative at the beginning there, it makes it where you can follow PEMDAS, okay? So we have the negative 2 and the negative out front. They're both going to affect the x. So we know we're supposed to multiply first, and since I did that common factor, I can follow PEMDAS now with my x's. So I know that that tells me I'm going to reflect across the y-axis. And then the x minus 2 tells me we're going to move 2 units to the right. So it's going to be a horizontal translation. Right 2 units. All right, and so the rule, we have x, y. That's going to become a negative x plus 2, whoops, didn't mean to, hold on, comma, the y value. So if we had the ordered pair, 1, 0, for example, then if I reflect across that y-axis, that's going to become negative 1, comma, 0, and then we're going to go to the right 2, so it makes this become 1, 0 as our final location. All right, example 8 says to describe how to transform the graph of f of x equals a natural log of x or y equals log of x into the graph of the given function. Describe the end behavior using limit notation. And so we have for A, we have g of x equals the natural log of x plus 2. So we know that that plus 2 is going to be a horizontal shift left 2 units. All right, so remember your parent log function had a vertical asymptote at x equals 0. If I'm going to the left 2 units, then my new graph here is going to have a vertical asymptote at x equals negative 2. Now my original one had a x-intercept at 1, 0, but I'm going to the right 2 units, left 2 units, so now I'm going to have a y-intercept, an x-intercept at negative 1, 0. So I'm going to go ahead and fill this in. So we said we had a vertical asymptote, and now at x equals negative 2, and we said our x-intercept is at negative 1, 0. Now if I just draw that in using those points, I can see that I also have a y-intercept I'm going to have to go find. So I'm going to go ahead and do that since I'm working on intercepts. So for the y-intercept, remember that's where our x is going to be 0. So here's our equation. Y equals the natural log of x plus 2. And so to find the y-intercept, we know our x is 0. So it gives me y is equal to the natural log of 0 plus 2, which is just the natural log of 2. So we have a y-intercept then at 0, comma, the natural log of 2. Natural log of 2 is an ugly decimal, so I'm just going to leave it as a natural log of 2 because that's nice and neat. Now, going back up, we can see that our domain, our graph does not keep going to the left, but it does go to negative 2, but it doesn't include it because that's the asymptote. And it does keep going to the right, so it goes to infinity. The range, our graph keeps going down, and it keeps going up. We talked about the asymptote. We talked about the intercepts. Concavity, We are increasing at a decreasing rate, so we are concave down. And then the end behavior. So the left-hand behavior says the limit as x approaches 0 from the right side, f of x equals, it's going to keep going down as it goes to the left there, so it's going to equal negative infinity. And then the right end behavior says the limit as x approaches positive infinity, f of x equals, and as we go to the right, the graph keeps going up, and it's going to keep going up to positive infinity. All right, B says we have 1 plus log of x, which remember, that's the same thing as saying log of x, and then plus 1. So we can see that plus 1 is going to be a vertical translation. And it's going to go up 1 unit. All right, so that's not going to affect my vertical asymptote by moving the graph up 1 unit. I did have an x-intercept at 1, 0, but now that's going to go up 1 unit, so it's going to be at that point 1, 1. All right, so I can kind of use that to help me draw. All right, so going through here, my domain does not keep going to the left, but it's going to start at 0 and not include it, but it does keep going to the right to infinity. My range keeps going down and it keeps going up. We said we still have that vertical asymptote at x equals 0. Now for the intercepts, we can see it does not have a y-intercept, but we do have an x-intercept. And so remember with the x-intercept, that's just where y is equal to 0. So we end up with, excuse me, 0 equals log of x plus 1. So I could subtract the 1. So we get negative 1 equals log of x, which I could rewrite that as log of x equals negative 1. I'm going to change that to exponential form because I can't solve for x here. To get rid of the log, I have to go to exponential form. So my base is 10. My y is negative 1 equals x. So x will equal 10 to the negative 1, which is the same as saying 0.1. So I have an x-intercept at 0.1, comma 0. Or you could say 10 to the negative 1, comma 0. We can see that this is concave down. It is increasing at a decreasing rate. And then our left-hand behaviors, the limit as x approaches 0 from the right. I just realized a mistake in the previous example. I'm going to have to go back and correct. I'm sorry, I'm too far in the video to start over. Not even f of x, this is h of x. Will equal negative infinity because it's going to keep going down. And then the right-hand behavior says the limit as x approaches infinity of, whoops, what do we say, this is h of x, equals, it keeps going up to the right, so it's going to keep going to infinity. And guys, I'm going to have to back up and talk about a for just a minute. I made a mistake here. And I can't pull back up what I had. So I'm just going to have to go back up to it. And I'm just going to draw it real quick here. So we had said we had that vertical asymptote here at negative 2. We had that x-intercept at negative 1. And we said our graph looks something like this. I'm sorry, I messed up on the behavior. For one thing, it's the limit, and it says x approaches 2 from the right. Should have been what I wrote there. And then I should have put g of x instead of f of x equals, and the negative infinity was still correct. And then on the right-hand behavior, the only mistake I made there was I called it f of x, and my function is g of x. And so I should have put g of x there because that's what it's labeled in the example. So I apologize for that. Like I said, I'm too far in the video to start over, though. So thank you for understanding. All right, then moving on to example 8c. So this is just saying the natural log of a negative x plus 3, which we can common factor out that negative there. So it's going to be a negative x minus 3. So we know that this graph is going to reflect across the y-axis. And then it's going to have a horizontal translation right 3 units. So if you just think about that, normally our graph, I'll do it up here at the top. So normally our graph looks something like this when we graph it. But now we're going to go across our y-axis, our graph is going to look like this. So that x-intercept that was at +1 is now reflected over on the other side, so it's going to be at -1, okay? So that'll help us graph it. So we still have our vertical asymptote. Actually, our vertical asymptote's not going to be there. Sorry. So let's look at this. So I was already talking about the x-intercept, so let's go with it. So it was at -1. Now we're going to reflect it across the y-axis. Try this again. It was at +1. Now we're going to reflect it across the y-axis, so now it's over here at -1. Then we said we're going to go to the right 3 units. So 1, 2, 3. So here is going to be my new x-intercept. Now, same idea. On 0 is where my asymptote was at. I'm going to reflect that across the y-axis, which means it doesn't move, but then I am going to move it to the right 3 units. I can't count, guys. I don't know what is wrong with me. I am so sorry. I'm going to try this again. I'm going to just start over, talking about how to find where the stuff is at. We know, let's go back to the x-intercept. Our x-intercept is originally at +1. If we're going to reflect across the y-axis, that means it's going to be over here at -1. And then I'm going to move it from -1 right 3 units. So 1, 2, 3. So now it's going to be right there. And that's what happens. I skipped the 0 earlier. So my x-intercept is going to be at 2, 0. My horizontal asymptote, not horizontal, vertical asymptote was at 0. If I reflect it across the y-axis, it doesn't move, it's still at 0. But then I'm going to go to the right 3 units. So 1, 2, 3. So now it's going to be right there. So I know that my vertical asymptote, telling y'all if I was not so far into this video. So the x-intercept was at 2, 0. The vertical asymptote is going to be at x equals 3. And I'm going to regraph that because I've made so many marks. So vertical asymptote at x equals 3. X-intercept at 2, 0. And we know because we reflected across the y-axis, our graph is going to look like that. Which means I can see there that I do have a y-intercept. So I'm going to go ahead and go find it. Remember, for the y-intercept, x is 0. So I have y equals, and it doesn't matter which form we use. I'm just going to use the natural log of -0 plus 3. So my y will equal the natural log of 3. So my y-intercept is going to be 0, natural log of 3. I can see the concavity is it's concave down. My range keeps going down, keeps going up. Now my domain, it keeps going to the left, so it's going to go to -infinity, and it goes into the right where that vertical asymptote is at 3, not included. So now my left-hand end behavior is going to be the limit as x goes towards -infinity. My function name is f of x will equal, and it's going to keep going up, so it's going up to +infinity. The right end behavior is the limit as x approaches 3 from the left, f of x equals, and at that point it's going down, so it's going to equal negative infinity. Wow. And so I am so sorry about the mistakes on this one. Hopefully you're okay with it. All right, example 9. It says an exponential function of the form g of x equals b to the x minus h plus k is shown in the table below. Use the table to answer the following questions. All right, so notice your x's in your table go from -4 to +8. Look at your g of x, your y values there. A says to describe the end behavior of the function. So we have the limit as x approaches negative infinity. You can see our function's name is g of x will equal, you notice it's getting closer and closer to 1. Then the other side, so the limit as x approaches positive infinity, g of x equals, when we look at it, it looks starting right here at the x is 4, we see the y is 3, 5, 9, 17, 33. They're just getting bigger and bigger, so they're going to go to infinity. B says, what is the value of k, and give a reason. So notice k is that vertical shift, okay? Our vertical shift is that asymptote, because we're in exponential form. So it's my horizontal asymptote. My graph is, we can see right here that horizontal asymptote is at 1. So that means that my k value is equal to 1, and that's because it is the horizontal asymptote. All right, C says output values change proportionally as input values increase in equal length intervals. Use this fact to determine the base for the g of x. So we can see let me clear out what I wrote some here. Move my circles. All right, so I know my x's are increasing by 1. I'm going to start with those whole numbers, like right here, okay? These are each increasing by 1. But notice what's happening to the y values. They're increasing by 1, 2, 4, 8, 16. So 1, let's say 2, 4, 8, 16. Notice all of those numbers have a base of 2. 1 is 2 to the 0, 2 is 2 to the first, 4 is 2 squared, 8 is 2 to the third, 16 is 2 to the fourth, and you can guess what the next one would be then, okay? So therefore, we know that our base is equal to 2. D says, use the point 4, 3, b, and k to find the value of h. Then write the equation for the function g of x. All right, so we remember that an ordered pair is just an x and a y. And so it told us up there at the top that our y is equal to b to the x minus h plus k. Well, I know my y is going to be 3 equals, we said our base was 2 to the x, which is 4, minus, we're looking for h, and then k we said was 1. Whoops, I meant to put a 1 there. And so we just need to solve for h. So first thing is, h is in that exponent, so I'm going to get that 2 to the 4 minus h by itself. So I'm going to move the 1 over. So I get 2 is equal to 2 to the 4 minus h. Now remember, we said that if we can get like bases, then we can get rid of the bases and set the exponents equal, that 1 to 1 property. So this is 2 to the 1 equals 2 to the 4 minus h. So that means that 1 is equal to 4 minus h. So I'm going to subtract the 4. So negative 3 equals negative h divided by negative 1. And so we know that h is 3. They did not give me a lot of room to write on this one. So what they told me there then is, I'm going to have to write it above here, that my equation that g of x is equal to, my base is 2 to the x, my h is 3, so minus 3, and then my k is 1, so plus 1. So I know we're not supposed to box, but I'm going to on this part. So there's my equation for g of x. 2 to the x minus 3 plus 1. All right, E, so state the domain and range of g of x. Well, it's an exponential function, so we know our domain, the infinity to infinity, and our range is going to be from that horizontal asymptote at 1 to positive infinity. All right, F. Let's see some, well, I can't see. All right, F says to find the inverse equation. So we know that g of x is equal to 2 to x minus 3 plus 1. So that's the same thing as y equals. So now it's going to become x equals 2 to the y minus 3 plus 1. So subtract the 1. And then I'm going to have to change it to exponential form. Well, let me see what's, dang. Let me see what's on this next page. I may have to come back to this. Hold on. Here, they gave me more room here. That was weird that they did that. All right, so we were on F. And so what we said we had was y equals 2 to the x minus 3 plus 1. And so then we switched our x and y. We're trying to solve for y, so we subtracted the 1. This is where I was at the bottom of the other page. Now, I'm stuck and I'm in exponential form, so I'm going to go to log form, but this is in that b to the y equals x. So I know my base is 2. The y on this one is my y minus 3, and the x is the x minus 1. So when I rewrite this, I have log base b of x equals y. And now just solve for y. So I'm going to add the 3. And so I end up with y equals log base 2 of x minus 1 plus 3. So the inverse of g of x is equal to that logarithmic equation there. And I know again we're not supposed to box. But there's my equation. All right, it says graph G and the inverse G on the same grid. So we've got the table there for G of X, and they gave us a table to set up for our inverse G of X. But remember, that's just going to be my X and Y's switched. So I'm just going to use like these points here. So I know 2, 3, 5, 9, 17. They give me 3, 4, 5, 6, and 7. I literally just switched the X and Y's around. All right. Now, so to graph my original function, I know, remember we said it had a horizontal asymptote at y equals 1. And so I'm just going to plot some of these points. So 3, 2, whoops, it's not 2. Oh, dang. Didn't catch that. These are by 2s. So 3, 2, 4, 3, 5, 5, 6, 9, 7, 17. So that's enough there. And so we have those points there. Then for the inverse, but remember that means there's that vertical asymptote now at x equals 1. 2, 3, 3, 4, 5, 5, 9, 6, and 17, 7. And so you can just imagine, we talked about that if we had that line y equals x going through our graph, remember they should be reflections across it. So if there's my line y equals x, does it look like my red and blue lines are reflections across that line? And it does. Oh, and then I didn't do the domain and range of the inverse. Well, we know that our domain is going to be from 1 to infinity. And our range keeps going up and down, so negative infinity to infinity. All right, and that is the end of lesson 10.